All right, so to go through a few examples or some further explanation, if we want to apply this to electrical fields, we're going to do very much the same as we did in the last video. We're going to kind of assume that this is like a classroom, but it's an electric field. So I have a plate that has a positive charge on it. I've removed a lot of electrons. And the bottom plate has a negative charge. So I've placed a lot of electrons on there. So they have opposite charges. So now we're going to go ahead and we need to figure out what direction should these arrows point in. So we don't use masses in an electric field. We use charges because an electric field acts on a charge, whereas a gravitational field acts on a mass. So here's where we run into an issue, however. If I place a positively charged object or a proton or something like that, and in between those two plates, well, the positive plate will repel that charge and the negative plate will attract it. So since the top plate is going to push it down and the bottom plate is going to pull it down, you can hopefully realize that this positive charge is going to get pulled downwards. The electrical force will be downwards. Repulsion by the positive plate, attraction by the negative plate. But if I place an electron, we'll say, with a negative charge, the opposite happens. The bottom plate repels it upwards, the positive plate attracts it upwards, and the force on that charge is going to want to go upwards. So depending on the type of charge I use, the arrows are going to go in different directions. So now we have a problem. Because gravity only is attractive, but because of this whole like attractive, repulsive, positive, negative, we have two types of charge as opposed to one type of mass, we have a little bit of an issue. So there's no real reason behind this other than we all needed to get on the same page. So moving forward, we need to recognize that when we want to draw electric fields, we must always use what is referred to as a positive test charge. Simply states that every physicist, everyone analyzing these fields, will assume that they tested the field with a positive charge, just so we're all on the same page. So understanding that we're going to be using that wherever I place this positive charge, you'll notice in this case, as we stated before, it's always going to get pulled downwards. Therefore, the electric field between these two plates will always point away from the positive and towards the negative. And that's simply just because we assume we're always using what's referred to as a positive test charge. So the field lines that you will see in an electric field diagram are the lines that represent the force that a positive charge will experience. So if you want to analyze what a negative charge will do in a field, you have to reverse everything. So the field lines themselves will always assume are the direction of the force acting on a positive charge. And it doesn't matter which way these plates are arranged. So just to show you a few other examples, you could flip the orientation of these plates, but what you'll notice about all four of those examples is that the positive plate always has the arrows pointing away from it, and the negative plate always has these arrows pointing towards it. And that's because the positive plate will always repel a positive test charge, and the negative plate will always attract a positive test charge. Now, when it comes to non-uniform electric fields, it's very much the same situation. So instead of looking at the Earth, we're going to place our positive test charge close to what we call a point charge. So it's not two plates anymore, it's just like a charged object. And if we think about it, two positive charges will repel. So that charge is going to get repelled away. If I place another positive test charge down here, again, it's going to be repelled. If I place a third one on the left, it's going to be repelled. So if we really think about our rules here, much like kind of when we drew the Earth in the previous video, the electric field will just be a bunch of lines pointing away. And that is because any positive charges placed near this positively charged object will be repelled. And that's what those arrows show. They show repulsion in all directions if you are a positive test charge. If we want to analyze a negatively charged object, we do the same thing. Again, we have to use a positive test charge. However, this time it would be attracted. Likewise, if I placed one down here, there's also going to be attracted. If I place one over on the left, that's also going to be attracted. So therefore, the electric field around a negatively charged object will simply be a bunch of lines pointing towards, because negative charges will always attract a positive test charge.